Electric vehicles are transitioning to 800-volt systems to minimize power loss and decrease charge times. However, higher voltages increase the risk of catastrophic electrical failures. If the physical insulation degrades, stray currents exceeding just 10 milliamps flowing from a high-voltage terminal to the protective earth ground become fatal to the user. To mitigate this risk, engineers integrate active insulation monitoring systems. These circuits must continuously monitor the system to detect resistance breakdown before a leakage path reaches dangerous levels. This creates a very difficult engineering tension. The monitoring circuit must be sensitive enough to detect minute leakages, yet physically robust enough to survive mandatory high-voltage stress tests without burning out. Designing an insulation monitor requires balancing measurement precision with component survivability under extreme voltage loads. This circuit calculates two unknown variables: insulation resistance at the positive terminal, R-ISO-P, and negative terminal, R-ISO-N. To solve this, switch 1 and switch 2 sequentially close, routing current through known resistance dividers, R-1 through 4, producing measurable voltage drops at the ADCs. A microcontroller captures these alternating ADC values to solve a multivariable system of equations. This process reveals the exact insulation resistance of the system. While this switching topology is mathematically sound in a diagram, it does not account for the extreme physical stresses these components face during real-world safety testing. Safety standards require manufacturers to evaluate insulation by performing a dielectric voltage withstand, or high-potential test. Under the IEC 60950 standard, a system must withstand a specific voltage load calculated as 2 times the maximum operating voltage, U, plus 1000 volts. For an 800-volt system, the final requirement demands a test voltage of 4,242 volts. During this test, the battery is removed, and a 4.2 kilovolt charge is injected directly across a terminal and chassis ground. This puts immense voltage stress on the open measurement switches. Because the certification process actively attempts to destroy the isolation barrier, the design priority shifts toward component survival. The primary destructive force acting on these switches during the test is avalanche current. The traditional protection method involves inserting large series resistors into the circuit to choke off the avalanche current before it reaches the switch. On the left, high series resistance protects the component but degrades the voltage reading, resulting in an inaccurate ADC measurement. To achieve accuracy on the right, lowered resistors yield a precise curve, but the excess avalanche current destroys the switch. This creates a direct conflict between passing mandatory safety certifications and achieving an accurate leakage reading. Legacy designs often rely on generic optical photo relays, but these components have specific physical limitations that complicate the design. Most generic photo relays are limited to an avalanche current tolerance of just 0.6 milliamps. Their performance under stress is restricted by internal constraints, specifically the switching speed of the integrated LED and its forward bias requirements. They also suffer from photo degradation over time and require external drive circuitry that increases the total solution size. Because these switches fail at low currents, designers are forced to use the large series resistor compromise just to prevent the relay from burning out. Solid-state relays offer an alternative. Instead of optics, devices like the TPSI 2140-Q1 use a resilient silicon dioxide capacitive isolation barrier. While a generic photo relay fails at 0.6 milliamps, the solid-state relay can withstand up to 2.0 milliamps of avalanche current. With over 3 times the current tolerance, the basic math of the circuit changes. Designers no longer require oversized resistors to protect the switch. Engineers can now lower the series resistance to match the insulation resistance, which preserves the precision of the ADC measurement. By increasing the current tolerance of the component itself, the circuit can survive a 4.2 kilovolt test without sacrificing measurement accuracy. We can see this implementation in a complete analog front end designed for electric vehicle charging and solar leakage measurement. This schematic shows the layout of the insulation measurement block. The solid-state relays bridge the boundary between the 800-volt high-voltage side and the 5-volt low-voltage logic. The path runs from the matched input resistors, R-stat-P and R-stat-N, directly through the relays and into the isolated amplifiers. This topology allows 5-volt controllers to safely and accurately sample massive 800-volt bus leakage. As electric vehicles and solar arrays move toward higher voltages to minimize power losses, the requirements for reliable, high-speed switching will continue to increase. Passing extreme safety certifications while maintaining sub-% measurement precision ensures the system remains functional and reliable under high-voltage stress. The future of safe high-voltage infrastructure relies on moving away from legacy components and adopting material advancements like capacitive isolation barriers.